This is part 2 on our section 5.2, perpendicular bisectors. When 3 or more lines, rays, or segments intersect in the same point, those are called concurrent lines, rays, or segments. The point of intersection of the lines, rays, or segments is called the point of concurrency. So the 3 perpendicular bisectors of a triangle are concurrent, and the point of concurrency has a special property, and that's what we're going to look at in this video. So theorem 5.4 is on the concurrency of perpendicular bisectors of a triangle. The perpendicular bisectors of a triangle intersect at a point that is equidistant from the vertices of the triangle. So let's take a look at that for a second. So there's your triangle, and we're going to have 3 perpendicular bisectors here. This segment DP is definitely a perpendicular bisector. It comes and intersects this side at a right angle, and it touches the midpoint D. We're going to do the same thing for point E. So segment EP is a perpendicular bisector. And segment PF, it's also a perpendicular bisector. Now, you have these 3 perpendicular bisectors, and they come together at this one point because they're concurrent. Now, here's what this theorem says, and it's super duper important. These lengths right here of these perpendicular bisectors, they are not necessarily the same length. When this is a scalene triangle, these will not be the same length. But here's what is the same. Look at these orange segments. Those orange segments are all the same length. So this point is the same distance from A that it is from B, and it's the same distance that it is from C. So we're going to use the concurrency of perpendicular bisectors. Hot pretzels are sold from point A, point B, and point E. Where could the pretzel distributor be located if it is equidistant from those 3 points? So we want to put the distributor somewhere here so it's equidistant to all of these. Well, how in the world do you do that? Well, I can't guarantee that I'm going to do it very well on here. But the first thing you should do is make a triangle. And if you were doing this on a piece of paper and pencil, it'd be a lot easier because you could use a straight edge. There's your triangle. Now, the next thing you're going to do is you're going to find the midpoint of every single side. And again, I'm just kind of freehanding this. I don't really know where the midpoints are. I'm indicating that they're the midpoints, but that's definitely not a guarantee. Then the next thing you need to do is come through here at a right angle. So we'll say that's a right angle. We'll say that's a right angle. And we'll say that's a right angle. And it actually didn't turn out too bad. So the idea here is when you draw your 3 perpendicular bisectors, they're going to cross at this point because these perpendicular bisectors are concurrent. Now here's what you know. This is what the theorem tells you. This distance from A to that special point is the same as the distance that B is from it. And it's also the same as the distance that E is from it. So the yellow lengths are the same. Now this is a good example to kind of illustrate what I talked about on the last slide. Would these red segments be the same length? Definitely not. Just because they're perpendicular bisectors doesn't mean they're congruent, but you use them to find a point of concurrency that is equidistant from those vertices. Okay, so that point of concurrency of the 3 perpendicular bisectors of a triangle, it's called the circumcenter. The circumcenter, P, in all of these diagrams, is equidistant from the 3 vertices. So P is the center of this circle that passes through all three vertices. So notice how if P is the center of the circle, P to any one of these vertices is going to be the same length because that's the radius of a circle. Okay, another thing to point out, well, it took me a long time to make this, but anyways, when you have an acute triangle, the point P is inside the triangle. That circumcenter is inside the triangle. When you have a right triangle, the circumcenter is going to be on the triangle, it'll be on the hypotenuse. And when you have an obtuse triangle, that circumcenter is actually going to live outside of the triangle.